Hello everyone, I am Vishal Nikam, working as an assistant professor at Department of Mathematics in Arts, Commerce and Science College, Onde, Vikramgarh, which is affiliated to University of Mumbai. Today we are discussing on the sequence of functions of real numbers. That is, in this video, we are highlighting that what is exactly mean by the sequence of functions, how these are related to the sequence of real number. Is there any relation between sequence of functions and sequence of real numbers? But in particular, we are discussing only on the sequence of functions of a real number. That is, the functions whose codomain is real number or subset of real number. Okay, so let's start. So these are the outlines of today's lecture. First of all, we will see the introduction, then definition of sequence of function, then what is mean by the pointwise conversion, uniform convergence, and test for the uniform convergence. Okay. The sequence of function is arrangement of images of function having the set of natural number is its domain, and what is its codomain? Let us see this figure. Here the function defined an of x. An of x, here are two variables, but we are defining only on the set of natural numbers. So for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. That is, this function maps 1 to one of this element. That is, suppose 1 maps to f of x, 2 maps to g of x, 3 maps to h of x, and 4 maps to k of x. Then the sequence of function is f of x, g of x, h of x, k of x, and so on. Or if 1 maps to g of x, 2 maps to f of x, then the sequence is g of x, then f of x, then h of x, and then k of x, and so on. That is what is mean by the sequence of function. That is some function defined from the set of natural number to the set which is subset of function, or to the set which contains the functions of real numbers, and the images of this function, the images of these functions are arranged in the natural order. That is, what is mean by the natural order? In the natural number 1, 2, 3, 4, 5, so on. That is, at the first place we arrange f of x, second place g of x, third place h of x, fourth place p of x. In this way, we are arranging the functions in the natural order. This is called what? Sequence of function. Okay. This is the definition of sequence of function. Sequence of function is nothing but the arrangement of images of a function whose domain is the set of natural number and codomain is set of function or subset of set of functions, or the set which contains the functions. Let A is equal to the set contain f of x and g of x, where f of x and g of x are any real valued functions. Now define phi n of x from n to a by phi n of x is equal to f of x if n is odd, and phi n of x is equal to g of x if n is even. Then the sequence of function is, what is phi 1 of x? Here 1 is what? Odd. Then phi 1 of x is what? F of x. Phi 2, 2 is what? Even. Then phi 2 of x is what? G of x. Phi 3 is again odd. So it is f of x. In this way, we are arranging, we have the only two elements in A, but we are arranging these two elements in alternating order by the rule phi n of x is equal to f of x if n is odd, phi n of x is equal to g of x if n is even. That is, we get this alternating sequence of functions. Now, in particular, if f of x and g of x are constant function, if f of x and g of x are constant function, then what happens? This, we get this alternating sequence of real numbers. A and B are what? Real numbers. So, by this idea, we can say that the sequence of real number is a particular case of the sequence of functions, isn't it? That is, by this idea, if this set A, that is, if the codomain What is the definition of sequence of function? It is a mapping, that is the images of a function whose domain is a natural number and codomain is set of functions. If subset of set of functions, if this codomain contains only the real numbers, then it is nothing but a sequence of real numbers, and here we get alternating sequence of real numbers. Okay. Next note, if f of x and g of x are constant functions, in particular take f of x is equal to 1 and g of x is equal to minus 1, we get 1 minus 1, 1 minus 1 is an alternating sequence. Here I think we get minus 1 to the power n plus 1. So we get the alternating sequence of real numbers. But this is not a sequence of real, this is sequence of functions, because 1 is not a real number, it is a constant function. It is again a constant function, right? Okay. So these are the some examples. You can see fn of x is equal to x upon n plus 3x square, whose domain and codomain are R. Fn of x is equal to x to the power n, whose domain is closed interval 0 1 and codomain is R. Here fn of x is equal to x upon n e to the power minus nx, whose domain is AB and codomain is R. Here fn of x is equal to cos nx, domain and codomain R, and again domain and codomain are R, and the sequence of function is sin nx upon n. Now here as n is a member of natural number, so here is no problem because n starts from 1 to n, so it is well defined function, sequence of function. Now next, definition of pointwise convergence. Actually the word convergence itself means that we are checking the convergence at each point of the domain. At each point of the domain. What it means at each point of the domain? If I am going to fix this point x or this point x, then it only depends on n. So it is what? If I am going to fix x, then it only fn of x is depend only on what? N. So it is a sequence of real number, and we can easily calculate the limit of the sequence of real number by n tends to infinity or by some mathematical rules, and we get the limit point for that particular x, for that particular x, which is a limit at that particular x. In this way, by varying x, we can calculate the limits, and finally we get a function. Finally, we get a function f from s to r, and which is called as a pointwise limit. How? By a particular example we can see easily. But what is mean by the pointwise convergence? Pointwise convergence is mean that by fixing x, we are finding limit of fn of that particular x. We are finding limit of n tends to infinity. Not, we are not varying x, we are varying n. We are varying n. And now limit as n tends to infinity. Suppose x is equal to c, then fn of c is a sequence of real number. Now taking limit as n tends to infinity, fn of c converges to some real number. So it is what? F of c. Now if instead of c, if I am placing some different point, suppose d, then fn of d as limit n tends to infinity, some converges to some point. This is called f of d. In this way, at each point of s, we are calculating limit, and this function is called as the pointwise limit. And if this function exists f of x, this is called a pointwise convergence of f of x. So this is an epsilon delta definition. A function fn of a real valued function is said to be converges to a limit f on s if for every x belongs to s and for every epsilon greater than 0, there exists a natural number here depends on x and epsilon such that fn of x minus f of x is less than epsilon for all n greater than or equal to n naught and depends on x and epsilon. Okay, x and epsilon. So this is we are calculating the pointwise convergence by using both the definitions. Firstly, we are calculating the pointwise convergence by using the epsilon delta definition, and for other examples, we are also calculating by using this definition also. So actually, to handle the pointwise convergence, this definition is beneficial or useful too, because the epsilon delta is used to verify that whatever you have calculated the limit is exist or not. By using this definition, we can never calculate the limit of the function or limit of the sequence, but we can verify that whatever calculated limit is exist or not. Yes, there are the two remarks, that is in the pointwise convergence, and not it depends on both epsilon and x, and it varies if I are going to change x. And these are the notation for the pointwise convergence. So this is the first example, defined from R to R by fn of x is equal to x upon n plus 3x square. When this is a sequence of function, let us check it has pointwise convergence or not. We know that 1 upon n tends to 0 as n tends to infinity. So 1 upon 3x square plus 1, 3x square plus n also tends to 0 by fixing x. By fixing x, that is for each x. If suppose someone take x equal to 1, someone take x equal to 2, someone take x equal to 5, any x, but for fixed x, 1 upon 3x square plus n tends to 0. Now I define the function R to R by f of x is equal to 0. That is, here we are assuming that this is an what? Pointwise limit of this sequence of function. And by using epsilon delta definition, we can show that this is an pointwise limit. That is, here we had assumed that this is a pointwise limit. For this we have to consider the absolute difference of fn of x minus f of x, which is equal to x upon 3x square plus 1 minus 0, because f of x is what? 0 function. F of x is what? 0 function. Now we know that, or we can see that 1 upon 3x square plus 1 is less than or equal to 1 by n, because 3x square plus n is greater than or equal to n, because x square is a positive number, 3 into x square is also a positive number, 3x square plus 1 is a number greater than n, because n is also a positive number. Hence, fn of x minus f of x is equal to mod of x upon 3x square plus 1. But 1 upon 3x square plus 1 is less than or equal to 1 by n. So this is less than or equal to mod x upon n. Now this is by placing or by considering less than epsilon, mod x upon n less than epsilon, we get this inequality, n greater than or equal to mod x upon epsilon. That is, fn of x minus f of x is less than epsilon if n is greater than or equal to mod x upon epsilon. That is, here we get a number to show that this inequality n greater than or equal to n naught. How we get n naught? Define n naught is equal to mod x upon epsilon plus 1. We get fn of x minus f of x is less than epsilon for all n greater than. That is, whenever you have to show that this limit exists for any given epsilon. Suppose if I am asking that is the pointwise limit exist or not, suddenly you can ask what is the epsilon. Then for that epsilon, you have to choose n, which is greater than or equal to n naught. What is n naught? It is difference on mod x and epsilon. X is your known value, lies between the domain, right? Mod x upon epsilon. Epsilon is given, so you can easily calculate n naught. So n is greater than or equal to n naught, then this inequality holds. So this is a pointwise convergence of this given sequence of function. So next example, fn of x is equal to x to the power n, defined from 0 comma 1 to r. Then let us check what is the pointwise limit of this function. If x is equal to 1, this is what? 1 to the power 1. This is constant sequence. Fn of 1 is equal to 1. That is, limit as n tends to infinity. Fn of 1 is also tends to 1. Now if x lies between 0 and 1, limit as n tends to infinity, x to the power n is equal to 0. Why? Because as mod x is less than 1, we know that the product of values become lesser and lesser. So limit as n tends to infinity, x to the power n is tends to 0, because the domain is what? 0 and 1, and here x is strictly less than 1, right? Thus we have the two values of f of x. That is, whenever x lies between 0 and 1, we have the limit of the function is 0, and for x is equal to 1, we have the limit of the function, sequence of function is 1, right? So is the pointwise limit of fn. That is the pointwise limit for this sequence of function is this function. F of x is equal to 0 for 0 less than equal to x is strictly less than 1, which is 1 for x is equal to 1. Now next example, let fn defined from closed interval ab to r by fn of x is equal to this function x upon n into e to the power minus nx. Then let us evaluate by the same method which is applied for the last example. When x is equal to 0, we have fn of 0 is what? 0 upon n into e to the power 0. This is 1. So 0 upon n is 0. 0 into something is 0. That is fn of 0 is a constant sequence which converges to 0 as n tends to infinity. Now if x is not equal to 0, limit n tends to infinity, fn of x is equal to limit n tends to infinity. Fn of x is what? X upon n into e to the power minus nx, which is 0. Why? Because x upon n into e to the power minus nx is less than or equal to 1 by n, and which is greater than or equal to 0 for all n greater than. So by sandwich theorem, we can say that this tends to 0. This is a constant sequence tends to 0. So this sequence is also tends to 0 as n tends to infinity. Hence, this fn of x tends to 0 function as n tends to infinity. Hence, the pointwise limit in both the cases x equal to 0 and x non-zero, the pointwise limit is 0. Let fn be a sequence of real valued function. Now we are going to discuss the uniform convergence. Now firstly we are calculating the pointwise convergence, then we are calculating or verifying the convergence is uniform or not. Now what is the difference between uniform convergence and pointwise convergence? Firstly, we are calculating the pointwise convergence for the given sequence of function, and then we are going to check is this convergence is pointwise or not. What it means, if the pointwise convergence is not exist for any sequence of function, then no need to check the uniform convergence. By default the uniform convergence fails. Okay, so the basic difference is that in the pointwise convergence, let us recall that the definition of the pointwise convergence. What is the definition of pointwise convergence? Yeah, that here epsilon delta definition. Fn of x minus f of x is less than epsilon for all n greater than equal to n naught, and n naught is depends on both x and epsilon. This is the basic difference. Here n naught depends on both x and epsilon, but in the pointwise, in the uniform convergence, the n naught is independent on x but depends on epsilon. That is the definition of uniform convergence is that let fn be a sequence of function of real values. Sorry, fn be a sequence of real valued functions. Here some printing mistake. Defined on S, which is subset of R, and f defined from S to R be a function. The sequence of functions fn is said to converges to f uniformly on S if for every epsilon greater than 0 there exists n naught belongs to capital N independent on x but depends on epsilon such that fn of x minus f of x is less than epsilon for all n greater than equal to n naught and for all x belongs to S. Hence we write fn converges to f uniformly. That is n naught depends only on epsilon and not on x. This is the basic difference between uniform convergence and pointwise. How it works? Let us see an example. Yes, we had just calculated that the pointwise limit of this sequence of function is this f of x for 0 if x lies between 0 and 1, it is 1 if x is equal to 1. Now we will prove that the convergence is uniform or not. Yes, firstly we had calculated this is the pointwise limit, and the pointwise limit is what? This function. For epsilon greater than 0, to check whether there exists and not belongs to capital R such that this happens, let x lies between 0 and 1, that is closed 0, open 1. Consider the modulus x to the power n minus 0, which is strictly less. This implies that x to the power n less than epsilon. Taking reciprocal, we get x to the power minus n is greater than 1 by epsilon. This implies that n into log x to the power minus 1 is greater than log 1 by epsilon. That is, n log 1 by x is greater than log 1 by epsilon. Hence, we get n is greater than log 1 by epsilon upon log 1 by x. Now here, see, as x tends to 1, here, what is value of x? X lies between these two numbers, 0 and 1. Obviously, x is not equal to 1. We can say that x tends to 1. Now, if x tends to 1, log 1 by x, sorry, 1 by x tends to what? 1, that is log 1 by x tends to log 1. Log 1 is what? 0. That is something upon 0 is infinity. So, n should be greater than infinity. That is, it is impossible to find an integer n naught which satisfies this condition, because n tends to infinity. So, we cannot able to find n which satisfies this condition. Hence, the convergence is not uniform. When this convergence is uniform, we have this condition x tends to 1. If we are decreasing or restrict our domain such that x cannot tends to 1, that is, if we have find the number a which is strictly less than 1, and fn is defined from 0 to a, then we can say that the convergence is uniform. Now this is a very important test for the uniform convergence. Let fn be a sequence of functions defined on a non-empty set S, which is subset of R, such that limit n tends to infinity fn of x is equal to f of x for x belongs to S, and define a sequence Mn is equal to this supremum of x belongs to S such that fn of x minus f of x, then supremum of mod fn of x minus f of x where x belongs to S, then fn converges to f uniformly on S if and only if the sequence Mn tends to 0. Now consider the part, that is, suppose fn converges to f uniformly on S. So what the definition of uniform convergence? For every epsilon greater than 0, there exists n naught belongs to capital N such that this condition gets satisfied. Fn of x minus f of x is less than epsilon for all n greater than equal to n naught and for all x belong. This is the definition of uniform convergence. Here, this epsilon only depends on n and not on n. This is true for all. For any given epsilon, we have to find only n naught such that this condition gets satisfied. Now, let n greater than equal to n naught and consider the set. Now, define the set with the help of this modulus fn of x minus f of x such that x belongs to. Clearly, epsilon by 2 is an upper bound because fn of x minus f of x is less than epsilon, is an upper bound from the above set from 1.1, 0.1, and hence the supremum of this k is exist. What it means? We have firstly defined this set. Clearly, epsilon by 2 is an upper bound for the set because fn of x minus f of x is less than epsilon. Is less than epsilon. Hence, the supremum of this set k exists. Let Mn is equal to supremum of x belongs to S such that Fn of x minus f of. Clearly, Mn is the least upper bound of k. Now, this implies that Mn minus 0, which is equal to mod of Mn, but mod of Mn is less than epsilon by 2 because epsilon by 2 is an upper bound for this set, which is strictly less than epsilon for all n greater than. What it means? Mn is less than epsilon for all n greater than equal to. By the definition of convergence of sequence of real number, we can say that Mn converges to 0. That is, by assuming uniform convergence of the sequence Fn, we proved that this Mn tends to 0. Conversely, suppose Mn tends to 0, then we have to prove that the convergence is uniform. Now, what is Mn? Mn is the sequence. Mn is equal to what? Supremum. Now if Mn tends to 0, by using the convergence of sequence of real number, there exists n naught belongs to n such that Mn minus 0 is less than epsilon for all n greater than n naught. This implies Mn is what? Supremum of this is less than epsilon for all n greater than equal to n naught. But Fn of x minus f of x is always less than equal to supremum of this, which is less than epsilon for all n greater than equal to n naught and for all x belongs to s. This implies that Fn of x minus f of x is less than epsilon for all n greater than equal to n naught and for all x belongs to s. Hence, by the definition of uniform convergence, the Fn of x converges to f of x uniformly. So let us apply the test for the uniform convergence to these examples. Just by using the epsilon delta definition, we had proved that this convergence is not uniform. Just apply the Mn test to check the uniform convergence of this sequence of function Fn of x is equal to x to the power n. For this, let us evaluate the sequence Mn. Mn is equal to what? Supremum of this Fn of x minus f of, but f of x has two values 0 and 1. So supremum of x to the power n minus 0 if this, because f of x is equal to 0 if x lies between this, and f of x is equal to 1 if x is equal to 1. Now here supremum of x to the power n and supremum, now both have the supremum value 1. Now here the supremum arises at x equal to 1, here the supremum arises at x is equal to 0. So in both the cases supremum value is 1. So the sequence Mn is nothing but the constant sequence 1 which converges to 1 which is not equal to 0, hence the convergence is not uniformly by using the theorem 1.1.11. Next example, let Fn defined from 0 to b, here the domain is 0 to b, and what is the sequence of function? X by n e to the power minus n. You can take any domain for this sequence of function, then Fn of x is the sequence of function on AB. Now let us check the convergence is uniform or not. Now by the reference of this example, just I think 1.1.8, yes, with the reference of this example, well, the pointwise limit is 0. Pointwise limit of this sequence of function is 0. Now let us evaluate the sequence Mn. X by n into e to the power minus nx minus 0, x by n into e to the power minus nx. Let us apply the minimization and maximization concept to find the supremum of this sequence. Let g of x is equal to x upon n into e to the power minus nx. Let us differentiate this function with respect to x and equating to 0, we get x is equal to 1 by. That is the extremum value of this function we get at x is equal to 1 by n. Now substitute x is equal to 1 by n here, we get g of 1 by n is equal to 1 upon n square into e to the power minus n into 1 by n. That is, we get 1 upon n square into e. Now limit as n tends to infinity, Mn tends to 0, hence the sequence Mn converges to 0. Therefore this sequence converges to 0 uniformly. Now let us take the sequence of function Fn of x is equal to n square x upon 1 plus n cubed x square for x belongs to 0, 1. Now if x equal to 0, obviously the sequence of function is 0 and converges to 0. Now if x is not equal to 0, then also we can check the sequence of function converges to 0 pointwise. Now let us check the convergence is uniform or not. For this, let us evaluate the sequence Mn, which is equal to this. We want to find the maximum value of the function. So let us take g of x is equal to this function, differentiate this and find x. So we get x is equal to 1 upon n to the power 3 by 2. That is, we get the maximum value at x is equal to 1 upon n to 3 by 2. Now substituting here, we get g is equal to square root of n by 2. Now limit as, that is, we get the sequence Mn is equal to under root n by 2. That is, this is greater than or equal to under root n by 2. Now limit as n tends to infinity, we can say that Mn never tends to 0 as n tends to infinity. Hence Mn is an unbounded sequence, and hence by Mn test the sequence Fn does not converges to f on this domain. Now if I change the domain, there might be possibility the convergence of uniform, that is, the convergence may be uniform. It might decrease or increase the domain. Now let us take another example. Fn of x is equal to sine nx upon n for x belongs to R. We have limit as n tends to infinity. Fn of x is equal to limit as n tends to sine nx upon n is equal to 0, because as n tends to infinity, this is some finite value, sine nx is some finite value, and this 1 by n tends to 0. So whole terms finite, some finite value into 0 is again 0. Hence this pointwise converges to the 0 function, that is limit as n tends to infinity sine nx upon n tends to 0 function as n tends to infinity. Now let us check the uniform convergence. For that, let us evaluate the sequence Mn. Mn is what? Supremum of Fn of x minus modulus of Fn of x minus f of x over x belongs to R. What is Fn of x? Sin nx upon n minus 0 sin nx upon n. Now what is the supremum value? This function sin nx has maximum value 1. So x belongs to R, sin nx has maximum value 1. So the supremum is 1 by n. Now hence we get Mn is equal to 1 by n. Limit as n tends to infinity, Mn is equal to 1 by n, hence limit as n tends to infinity, 1 by n tends to 0, hence by theorem 1.1, the given sequence of function fn of x is equal to sin nx upon n converges to a 0 function uniformly. Hence these are some examples of the sequence of functions. So in order to clarify the concept, I will give a tutorial. For this tutorial I will provide the link in the description. You can go through that. Thank you.